And here we are in College Algebra, Chapter 2, Section 5, where we're going to talk about transformations of functions. These are often referred to as parent functions. And let's take a quick look at these. This is a constant function on the left here, and it graphs as a horizontal line, and you're seeing this notation f of x equals c. In other words, y equals c, and this might be the graph of the line y equals 1.5 or 1.6, where all of the points on the graph have the same y coordinate. And below the graph is listed the domain and the range, and a function like this can receive any x value as an input, but for this particular function, you are constantly going to get the same output value of c, or whatever your constant value happens to be, 1.6 maybe in this case. The next one is the identity function, y equals x. Again, you can plug any value in for your x value. You'll get the same value out as your y value in this particular function, and we're going to be modifying some of these, no doubt. And as far as the range is concerned, you're going to get all of your possible output values as you plug in all of those potential domain values. So you see that the graph dives down to the left, and it does continue going all the way down as it goes all the way to the left, and similarly up and to the right. Remember that domain and range are lists of x values and y values that show up on your graph. Another way to say that is that the domain of a function is a list of all of the x values that you are allowed to plug into your function, and the y values is the list of all of the range is the list of all the y values that would come out of your function. This particular function is increasing on the entire domain, so from negative infinity to positive infinity, as we move from left to right, our y values are increasing. In this basic version of the absolute value function, you can plug in any x value you want, but the range values, the numbers that are coming out of this function, only go so low as 0. This graph does pass through the origin, so it does actually have a point on the graph with a y value of 0, which is why if you look at the range, you see that there's a square bracket or a closed bracket to the left of the 0, and that's because 0 is one of the y values that we attain, and then it goes up from there. We would say that in a way, the left-hand side of this graph is decreasing, because as you move from left to right, you're going, I like to think of it as going downhill. And then once you reach this turning point, the remainder of your graph, you'll be going uphill. Your y values will be increasing as opposed to decreasing. Notice that in these comments right here about increasing and decreasing, that the 0 has a parenthesis or an open bracket here and here. So based on this description, it looks like our function is neither increasing nor decreasing at that vertex, at the very bottom of this V-shaped graph. And that's not an accident, that's correct. This would also be considered an even function, the absolute value function, because it is symmetrical about the y-axis, or symmetric about the y-axis. We could pick a point anywhere on the graph, and if we go a certain distance over to the y-axis, and then we travel that same distance to the other side of the y-axis, we will land at another point on our graph. That's one way to explain what symmetry about the y-axis means. Now, our identity function is an odd function, but it's not a great graph to give an explanation of what symmetry about the origin means. So I'm going to hold off until we look at our next function. Well, okay, so not this function, but we will see another function where we can talk about symmetry about the origin. This is your standard quadratic function, y equals x squared. You can plug in anything you want, but notice the range again starts at 0 and goes up. Your function's decreasing from negative infinity to 0, and I'm talking about x values now. As we move from left to right through our x values, our y values are decreasing down to 0. Our function here is neither increasing nor decreasing at its vertex, and as you move to the right, it is increasing. It's an even function because we have that symmetry about the y-axis, which I like to think of as sort of butterfly symmetry or book symmetry. That's what makes it an even function, or one of the characteristics of an even function. The square root function as a parent function lives in the first quadrant. Remember, your quadrants are 1, 2, 3, and 4. So square root lives in the first quadrant. As far as domain values, you can take the square root of 0. So 0 is an acceptable domain value, or any other positive number. And when I say number, I don't just mean 1, 2, 3, 4. I mean 16/17. The square root of 7 would be a valid input value into the square root function. Absolutely any number from 0 or greater. That's our domain, and the range is identical. The square root of 0 is 0, so that's the beginning of our range, and then our y values increase from there. So our function is increasing on its entire domain. It doesn't have symmetry about the y-axis nor the origin, so this function is considered neither even nor odd. The cubic function, y equals x cubed, does have symmetry about the origin because it's an odd function. And what symmetry about the origin means is that if you pick a point on your graph, let's choose this point at 1, 1, and we travel to the origin, and then we continue in the same direction, the same distance again, we will arrive at another point on our graph. And you could do that process starting from any point on your graph. You could travel through the origin and then in the same direction for the same distance, and you will end up at another point on your graph. So that is a characteristic of an odd function, and we describe that as symmetry about the origin. You can plug in any x values you want, so the domain goes from negative to positive infinity, and as this curve goes down to the left, it will continue all the way down to negative infinity, and as it increases to the right, it goes up to y values of positive infinity, so the range is also all real numbers. But when we talk about increasing, notice that as you move from left to right on this function, it is always progressing in the upward direction. So we say that this function is increasing on the entire domain. On the right-hand side of your screen here is the cube root function. And this function looks kind of similar to the cubic function. And they are indeed very similar. They are reflections of one another over the line y equals x. So if we were to take our graph and sort of fold it over or mirror it over this line y equals x, the resulting graph would be the cubic function. And vice versa. Take the cubic function, reflect it over the line y equals x, you would get the cube root function. That's happening because these two functions are inverses of each other. You don't need to know that right now, but I thought I'd plant the seed, put it in your mind, because we will hear that kind of language farther down the road. Domain, range, it's increasing everywhere. As we move from left to right, the y values are increasing, and it does also have symmetry about the origin because it is an odd function. Now, if you're one of my students, then you have access to these printable notes. So I would highly recommend, instead of writing all of this down, you might want to actually print this page and maybe tape it into your physical notebook, because we're going to be taking these parent functions and modifying them as part of our conversation about transformation of functions. What kind of transformations are we talking about? Well, the first one would be a vertical shift. And a vertical shift happens when you take your original function, f of x, and you add or subtract a value from it, or to it, or from it. And if you're adding a value to the outside of your function, it will move the graph of your function in an upward direction, as depicted here. And if you subtract a value from the outside of your function, it will shift it down. So the black curve that you're seeing is the original function, and then the blue curves are your vertically shifted graphs. Sometimes PDFs don't take equal signs very well, so realize that this should say y equals right here if you want to put in the other part of that equal sign. Down here it looks like kind of a really thick minus sign or something. That should also be an equal sign. And to the right of where it says f of x down here, this should say minus, because we have shifted our graph in the downward direction. So that's a vertical shift, and vertical shifts can happen in the positive or negative vertical direction. A horizontal shift is caused by adding or subtracting a value to the inside of your function. Notice that those plus and minus c values are happening inside the parentheses or inside the function. And a tricky part about these is, let's have a look at this first graph. This says f of x plus c, but notice that our original graph has moved to the left a distance of c. Similarly, in our second graph, where it says f of x minus c, our graph has moved in the positive horizontal direction. So when you see a modification inside of a function, be aware that the resulting transformation is going to be maybe kind of backwards from what you would have anticipated it being. I often refer to it as being counterintuitive. Another transformation that we see is where we take, in this case, our parabola, which is drawn in black, and after it's reflected about or over the x-axis, we see the parabola is upside down. The vertex hasn't changed, but our parabola has been mirrored over the x-axis. And that happens when you negate an entire function. And that's not a big surprise, because our original function was generating our y values. And here's that function that was generating those y values. And this minus sign is negating all of those y values. So you can see on our graph where we have here in the top left, in the second quadrant, we have a y value of positive 4. That corresponds to this point down here that has a y coordinate of negative 4. If our original graph had a point below the x-axis, its reflection about the x-axis would have resulted in that point appearing above the x-axis. So anything that was above becomes below, and anything below goes above. Anything that's on the x-axis, like this parabola, has a vertex that's at the origin, which is on the x-axis. You don't see a change in that one. That one's just sort of folding over on itself and does retain that y value of 0. I've already drawn in the equal signs, and somewhat poorly, I'll be happy to admit. This should say y equals, and this should also say y equals. And what's happened here is we've introduced a negative sign inside the function. And the graphical result of that, our original function is graphed here on the left. It's the cube root function. And by introducing a negative inside the function, we have caused a reflection over the y-axis. Notice that this point is at 8, 2, and it corresponds to this point, -8, 2. So we have negated our x values, and that's exactly what you're seeing in here. In our first example question, we're being asked to express in words how our standard quadratic function, f of x equals x squared, would be transformed when written as h of x equals this function. So there are a few different things that are happening here. One is there's been a positive 2 added, that's not a bracket, I don't know what that was. There's a positive 2 that's been added to the inside of our function. There's a 1 that's being subtracted from the outside of our function. And there's been a negation of the entire function. That negative sign's appearing outside of the squaring process. So what are the graphical sort of results of this kind of a transformation? For one, and I would tend to do it in this order, for one, this negative sign is going to flip our graph or reflect it about the x-axis. Secondly, the addition of a 2 inside our function is going to cause a horizontal shift in which direction? To the left or to the right? It says +2 in there, so is it going to move in the positive horizontal or negative horizontal direction? Remember, when there's a modification like this inside the parentheses or inside of our function, the result is counterintuitive. This is actually going to shift our graph to the left 2 units in the negative direction. So I've written left in caps there. So that's the second transformation that I would perform. And then the last transformation I would make is this one. This is a vertical shift, so it's going to move us either up or down. And which one do you think it is, up or down? This one outside the function is intuitive. It says -1. It's going to move us vertically down 1 unit. So it's a vertical shift in the negative direction. Down 1 unit, left 2 units, x-axis rotation. I don't love that it says rotation. The typical language here is reflection. So down 1 unit and left 2 units is correct, and x-axis, please change in your notes to say reflection. That is more typical language. B is our correct answer. And let's see what our next example has. Oh, it's not an example yet. There are more transformations we need to talk about. A vertical shrink or stretch is exactly that. Visually, that's what appears to be happening. Our blue curves in these graphs are the original curves. The one on the left, we have caused a vertical stretch because we're using a c value that's larger than 1. In other words, we're multiplying our original function by a number that's greater than 1. And remember, f of x was the original generator of all of our y values. Those are the up and down numbers, right? Our y values. And this number c right here is coming in and multiplying those y values by something larger than 1. So the y values are going to get bigger. We're not modifying the x values. You'll notice neither one of these graphs have gotten wider or narrower. They've only gotten either taller or shorter. So we've taken all of our y values and multiplied them by something. X values are staying the same. So a C value greater than 1 causes a vertical stretch. A C value that's between 0 and 1, for example, 1/2, 1/3, 2/5, that's going to make all of our Y values smaller, and it's going to look like we sort of smashed our graph from the top and from the bottom. And you can see that the stretch did multiply our negative Y values and make them more negative, in addition to taking our positive Y values and making them more positive. The same thing's happening for a shrink, except that our negative Y values are getting less negative and our positive Y values are becoming less positive in a vertical shrink. But again, our X values did not change for any points on those curves. Now a horizontal stretch or shrink, that is going to be messing with our X values, but not our Y values. Notice neither one of these functions or curves have gotten any taller, but they have either gotten wider or narrower. So for a vertical shrink, let me actually back up just 1 second and just highlight. We talked about it, but I didn't really point it out. The vertical stretching or shrinking happens when we multiply by a number on the outside of our function. I mentioned it, I said it, but I didn't highlight it. Now I'm highlighting it. Your C value is here on the outside of your function, regardless of whether it's between 0 and 1 or if it's greater than 1. This is a multiple that's happening outside the function, causing a vertical stretch or shrink because it's modifying our Y values, our f of x values. A horizontal stretch or shrink, look where our C value is this time. Now our C value is inside the function. It's right next to that x value. So obviously, I hope obviously, our C values modifying our x values. Whether it's a horizontal stretch or a horizontal shrink, the C value is multiplying inside our function, and as was the case when we were adding or subtracting inside the function, it's counterintuitive. So if I use a C value that's greater than 1, do you think it causes a horizontal stretch or shrink? You might think it would stretch it because it's multiplying our x values by something like 2 or 3. But it's kind of backwards. Here we've got a C value that's greater than 1. Our blue curve is our original function f of x, and the red curve, even though it's a C value greater than 1, has become narrower. We have compressed in from the sides, and that's from both sides. Look, it got narrower from the left and from the right. And for a horizontal stretch, we're using a value again like 1/2 or 1/3, something between 0 and 1, and it ends up giving us a graph that's wider than the original. This is another table that you might want to have printed and taped into your notes. Printing from a screenshot here is probably not a good idea. From the original PDF would be better. And I'm taking a quick look to make sure that all of the equal signs are there. And it looks like they are. And I put these brackets and numbers on the left-hand side because this is the order in which I recommend you do your transformations. Do your horizontal and vertical stretching first. And then, if there are any negatives in there that cause you to reflect over the x or y axis, do those reflections second. You could interchange numbers 1 and 2, but you definitely don't want to do those after doing number 3. You want your vertical or horizontal shifts to happen last. Let's look at this example where we have to do the modifications graphically on our own and not just describe them using words. The parent function here is the absolute value graph. And instead of using this sort of graph paper that was given to us, I'm going to draw some sketches so that we can see this thing play out. Again, our horizontal or vertical or horizontal stretch or shrink is what I recommend doing first, and that's going to be caused by the number 2 here. So that's what I'm going to do first, and then the second thing that I'll do is I will apply this negative. The negative outside the function is going to cause a reflection over the x-axis, so that's number 2. The third thing I'll do is I'll deal with that plus 3 in there, and the fourth thing I'll do is work with the 2 that's happening on the outside of the function, the addition of the number 2. So we're doing horizontal stretching and reflecting first, and then we're doing vertical and horizontal shifting second. This is our parent function, the absolute value of x. Bad. Much better. All right, so that's the absolute value of x. Now, let's use that multiple of 2 that I labeled first, and we'll say that this function is f of x equals 2 times the absolute value of x. That's going to cause a vertical stretch, which will make our absolute value graph taller. So we've multiplied all of our original y values by 2. The next thing I'll do is, as I've labeled number 2, we'll do the vertical reflection over the x-axis. It's still fairly narrow. It's now just getting taller in the negative direction instead of taller, faster in the positive direction. And this function is f of x equals negative 2 times the absolute value of x. And that was a reflection over the x-axis, or a vertical reflection. And then we need to incorporate the third element. So this is 0, our parent function. This is after our first modification. This is after our second modification. And then let's move over here to do our, maybe we could go down here. Our third modification says plus 3 inside our function. Remember that that's kind of backwards because it's happening inside our function. It's going to cause a horizontal shift because we're modifying our x values, but it's not going to go in the direction you might think. It's going to move in the negative horizontal direction. So we're going to move our absolute value graph to the left 3 units. 1, 2, 3. And if you want on the negative vertical axis, 1, 2, 3, 4, 5, 6 is where it's actually going to go. So it's still got that narrow kind of a feel to it. It looks a little bit wider than I'd like here, but it is this same graph. We've just shifted it to the left 3 units. This is f of x equals negative 2 times the absolute value of x plus 3. So we're seeing how these transformations play out one at a time, and this is after our third modification, which is a horizontal shift. And then let's go to our last transformation. Number 4 is that plus 2 that happened on the outside of the function. That's going to be modifying our y values. It's going to be adding 2 to them. Our vertex has moved up 2 units. Our y-intercept has moved up 2 units, so it's crossing the y-axis at -4 now instead of -6. And this is number 4. This is a horizontal shift. And this is the graph of g of x. Ooh, let's write in our function. We could call it g of x now, I suppose. G of x equals -2 times the absolute value of x plus 3 plus 2. I hope that gives you a good feel for your transformations. Remember that if there's a modification happening inside your function, it's modifying x values, and the graphical impact is counterintuitive. If it's happening outside your function, it's modifying y values, and it's going to do what you would think it's going to do. Make sure that you're performing your transformations in the correct order, and if you take it step by step, you should get lots of right answers. I will see you in the next section. Thanks so much.